So we'll talk, we'll recall what we were talking about last time, just, a brief reminder. We were talking about the regulation of glomerular filtration rate, glomerular filtration rate by two different mechanisms. One mechanism, responds to the changes in the blood pressure, myogenic. Essentially, when blood pressure increases, the stretch of the blood vessels increases as well, and that leads to constriction of afferent arterioles, dilation of efferent, decreased blood flow, and decreased GFR. And the response to low blood pressure is the opposite. And we also talked about tubular mechanism, in which blood vessels, the afferent arterioles, respond to the changing concentration of sodium. When GFR increases, the filtrate moves through the tubular system of the nephron faster, which decreases reabsorption time. That increases the concentration of sodium chloride in the filtrate, which is sensed by macula densa cells. Macula densa cells signal to the granular cells to constrict the afferent arteriole, and GFR decreases. That makes sense. So that's regulation of glomerular filtration rate. Now this, I'm really proud of that flow chart. It shows, it shows all the intricacies of the regulation of the GFR. Now I want to break it down, and we're going to trace down all the responses, okay, that change the kidney perfusion in response to how kidneys regulate blood pressure. So you can imagine that the main responses associated with kidneys will be taking care of the blood pressure that is lower, for instance, in a situation of dehydration or blood loss. Does that make sense? So say blood pressure decreases due to the blood loss. There are several ways. Systemically, it will lead to the activation of the sympathetic nervous system. Sympathetic response will lead to the release of norepinephrine and epinephrine. We're clear? So both these hormones will lead to vasoconstriction, which will lead to elevated blood pressure, not only because just vasoconstriction leads to the elevated blood pressure, but also, if you think about it, vasoconstriction, systemic vasoconstriction, how will it affect kidney perfusion? How will it affect the blood flow through the kidneys? Decrease it. Blood flow through the kidneys decreases, meaning less urine is produced, blood volume will increase, so on and so forth. Does that make sense? Okay, so that is exemplified here. Afferent arterioles will be constricted, urine volume will decrease, blood volume will increase. Another response that is going to be mediated by kidneys is mediated by juxtaglomerular or granular cells. In response to sympathetic activation, juxtaglomerular cells will release renin directly. Renin will activate angiotensin. Angiotensin will lead to the release of aldosterone from the adrenal cortex, and aldosterone will increase retention of sodium, followed by retention of water. All of it will increase blood volume. Does that make sense? Now, decreased blood volume will also reduce the stretch of afferent arteriole. The result of it, release of renin as well. Okay? Now, think about what happens with the rate of the filtrate flow in the kidneys when blood pressure decreases. When blood pressure goes down, say there is a loss of blood, what's going to happen to the amount of blood that goes to the kidneys overall? Less blood meaning less flow to the kidneys. Does that make sense? Less flow to the kidneys, less filtrate is produced. Less filtrate is produced. Filtrate flows slower. Does that make sense? As it flows slower, there is more time to reabsorb sodium chloride. So concentration of sodium chloride in the filtrate will go down. Macular denser cells will sense it, signal to juxtaglomerular cells, and juxtaglomerular cells will release renin. Does that make sense? And finally, there is a response from kidneys directly. Response to reduced stretch, they will produce adenosine and prostaglandin, which will lead to vasoconstriction. Now, all this complexity can be actually categorized in two distinct responses. One response is mostly vascular. Okay? So think about this. When blood pressure goes down, what happens to the stretch of the blood vessels? It decreases, right? Stretch decreases. Now, in response to that decreased stretch, or in response to systemic activation, what happens in the kidneys is vasoconstriction, decreased blood flow, increased blood volume, elevated blood pressure. So this is what we can call a vascular response. Does that make sense? It is not mediated by any hormones. It is in response to blood vessels being stretched or not. Then you have norepinephrine, epinephrine, okay, that will also cause vasoconstriction. Does that make sense? And finally, you have renin-mediated responses. Does that make sense to you? So we've got sympathetic responses and we've got renin-mediated responses. Sympathetic responses will mainly deal with the vasoconstriction, while renin-mediated responses will induce the retention of sodium and water. We're clear? We're going to come back to that topic again when we will talk about the balance of electrolytes. So that brings us from the process of filtration to the process of renal reabsorption. One thing to remember, and remember very clearly, is that in reabsorption, ions and organic molecules move from filtrate into the blood. Okay? Does that make sense? So reabsorption can occur by several ways. Well, first, we can see if the compounds that are being reabsorbed go through the membranes of the renal epithelium, or they move between the cells. So the route, which includes a transport of compounds through the membranes, is called transcellular route. The route that involves the transport of compounds between the cells is called paracellular route. Before we move any further, I want to discuss with you both routes. And we're going to start with transcellular. So let me ask you this. Filtrate. What is the main component of it? Water. Very good. Water. So compounds that are in the filtrate, are they water or lipid soluble? Water. There's going to be a series of pretty stupid questions. Okay. Water soluble. So when these compounds from filtrates are reabsorbed back into the blood via transcellular route, they have to cross something. Some really good barriers. Can you see those two barriers? What do we call those two barriers? The M word. Membranes. So you have two membranes. The apical, my bad. The apical membrane and the basal membrane that water-soluble compounds have to cross. Can water-soluble compounds cross those membranes directly? No, they can't. What do they have to have in order to cross the membrane? How water-soluble compounds can cross? No. To cross the membrane. Pump, that will work. What else would work? If it's pump, what kind of transport it's going to be? A word. Active. Can they cross via passive transport? Well, yeah, but can they? Do they have to have something in order to cross the membrane by diffusion? They do. What do they have to cross the membrane? They're water soluble. Membrane doesn't permit water soluble molecules to go through directly. What do they have to have? Channels. So they either gotta have channels or pumps, but either thing would work, right? Does that make sense? So they gotta have some protein. Either pump or channel or transport or whatever you want to call it. Makes sense, right? So they can cross either by facilitated diffusion or by active transport. Are we clear? Is that understood? Now take a look at paracellular route. Water, solutes, do they cross the membranes? During paracellular, they go between the cells. Between the cells. No. Between. Like they don't really cross the membrane. So they cross the junctions, but not the membrane itself. Okay? So it's like squeezing through the really, really narrow fissure. Does that make sense? So since they don't cross the membranes, do they have any pumps or channels on their way? So what kind of transport these molecules of water or solutes can use if they take paracellular route? It's only one. It's a D word. Diffusion. They can't do active transport. There are no pumps and there's no membrane, right? There's no membrane to put the pump in. So basically this is the idea. Transcellular route can be both active transport or diffusion. Paracellular route can be only diffusion. Does that make sense to you? Now, what I think is lovely in the renal system is because it's basically a summary of what you have learned already. And the mechanism of reabsorption, we're going to chat about it. And then you're going to tell me if you have heard about it before. Okay? So look at the picture in the left bottom corner of the slide. So here you have blood, and here you have filtrate. Look what is present at the basal membrane of the tubular cells. It's a sodium-potassium pump. Is that understood? So it pumps sodium out of the cell, right? Pumps, remember it's ATP involved, okay? Pumps the sodium out of the cell. So how does it affect the sodium concentration inside of the tubular cell? It keeps it what? If the pump pumps the sodium out of the tubular cell, what will be sodium concentration inside the cell? Low. Does it make sense? It's going to be low. It's going to be lower than in the filtrate. Are we clear? That makes sense to you? Which means sodium will be able to diffuse through the apical membrane. Okay? So on the basal side, sodium is actively transported in the blood, which maintains low sodium concentration inside tubular cells, and that enables sodium to diffuse from the filtrate in the tubular cells. As sodium diffuses into the tubular cells, what happens to it? It gets... So sodium from filtrate gets into the tubular cell. And where does it go from the tubular cell? To the blood, this time by active transport. So that chain of active transport at the basal membrane and diffusion at the apical maintains the constant flow of sodium from the filtrate into the blood. Does that make sense to you? Did you see it before? I bet you did. Do you remember which system? At least it sounds familiar. That's good. Huh? See again? No. Digestive. Sodium uses the same absorption mechanism works in the intestines for the sodium absorption. Does that make sense? I'm going to ask many more times. Do you understand that idea of sodium being actively transported at the basal membrane, which allows it to diffuse at the apical? So we've got covered sodium reabsorption. What follows sodium? How do we call the process of water diffusion, quote unquote? Osmosis. So water gets reabsorbed from the filtrate. As water leaves filtrate, what happens to the concentration of other ions in the filtrate? They increase. So chloride concentration increases, right? Chloride gets passively reabsorbed. Does that make sense? Just because its concentration increases, it can diffuse from the filtrate into the blood. Does that make sense? Urea concentration increases, so urea diffuses back into the blood. Are we clear? So the idea is that basically in the beginning, if you would look at the levels, say for chloride, that's the filtrate, that's the blood, that's the concentrations. And after water reabsorption, the concentration in the filtrate will go up and then the blood will remain the same. So now chloride can get reabsorbed. Does that make sense? Now before we discuss this wonderful graph, I want to ask you if anyone remembers what the secondary active transport is. I'll remind. So take a look at the apical side of the peritubular epithelium. what kind of transport is used by sodium here? We just discussed it. Apical side. Hold on. Apical side, you see? Diffusion. Sodium diffuses into the tubular epithelium. Are you with me? Well, you probably have learned that this is my depiction of diffusion, right? So sodium ions are moving down the concentration gradient, and do they gain some energy as they're moving? Yeah, what kind of energy? Kinetic energy, right? There are special proteins that can harness the kinetic energy of moving sodium ions. So that energy can be used to move other compounds against their concentration gradient. Does that make sense? This is called secondary active transport. Are we clear? For instance, sodium calcium symporter will provide a way for calcium to get into the cell, back into the peritubular capillaries. Yeah, well, eventually. Sodium amino acid symporter will do just the same. Sodium glucose symporter will do just the same. Does that make sense? Now, before we move any further, I want to put it in a perspective with you. And to do this, I'm going to make a bit of a drawing here. So let's talk again about the reabsorption in the renal tubules. Those are epithelial cells, okay? This is capillary at the bottom. And filtrate is right here. Okay, let's just graph this whole story, okay? We're not going to do it for glucose, amino acids, blah, 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 whatnot. No. We're going to do it for sodium, water, maybe chloride, potassium, stuff like that, okay? We're good? So let's chat. First, let's talk about sodium. What kind of transport moves the sodium from the tubular cells into the blood? Active transport. Active transport. So that's active transport. That's the sodium-potassium pump. Does that make sense? Let's keep potassium in mind, shall we? We're going to chat about it for a few seconds at the very end of this discussion. Now, since sodium is being pumped out of this cell, what happens to the sodium concentration inside of the tubular cell? It is maintained low. Tiny, low sodium concentration. The concentration of sodium in the filtrate, though, is higher. So on the apical side, sodium will be what? It will diffuse into the cell. Are we clear? Now this diffusion will attract which another molecule? Water. So water will follow sodium via osmosis. Does that make sense? But not only this, sodium, since it diffuses, that diffusion provides a source of energy that allows the reabsorption of molecules that will have to go against the concentration gradient, such as, I'm just taking glucose as an example. So this processes sodium diffusion and glucose reabsorption. They are coupled. Does it make sense? Do you understand what I just said? So sodium diffusion into the epithelial cells is necessary for glucose reabsorption. Are we clear? So far? You good?
Can you say the last thing?
So sodium diffusion and glucose reabsorption are coupled. When processes are coupled, one is required for another. Sodium diffusion is required for glucose reabsorption. And this glucose, this is an example of secondary active transport. So energy harnessed from sodium diffusion will be used to move glucose against its concentration gradient. Does that make sense to you? Now on top of that, as sodium, glucose, water, most of all water, they leave filtrate. What happens to the filtrate concentration? When water leaves filtrate, filtrate concentration goes up. And that allows for, say, passive reabsorption of, for instance, magnesium. Okay? That make sense?
Okay, so the concentration in the filtrate is up.
When water gets reabsorbed, yeah, concentration goes up.
So
Magnesium concentration will start to rise compared to the, so magnesium concentration in the filtrate will start to rise compared to magnesium concentration in the blood. So it will go high to low. The challenge that I face every time when I do this, when I do the drawing like that, is that what we do here, we draw a static picture. Does that make sense? Like, it looks like there are two vessels, the non-moving blood and non-moving filtrate. Does that make sense? You have to remember, filtrate is constantly flowing, and the blood is constantly flowing. So these reabsorption events, they happen in different parts of the peritubular capillaries. Does that make sense? So it's very dynamic process. And the concentration of filtrate will be changing along the proximal convoluted tubule or nephron loop or the distal convoluted tubule. Are we clear? Does that make sense? The concentration of filtrate constantly changing. I wanted to say something really smart and forgot. Oh, potassium. You see how I avoided it? That sodium at the bottom. The process of sodium pumping into the blood. This process is coupled with what? Potassium pumping into the cell. Do you know any foods rich in potassium? Bananas. What is the way to execute a capital punishment in the United States? Potassium chloride. So, can you commit suicide by eating 2 pounds of bananas? No. You know why? Well, because potassium, it's not immediate. Like, you can commit suicide by injecting, potassium chloride IV, but if you think about it, like, what's the difference? You eat like 2 pounds of bananas, your blood potassium should skyrocket and you should die because of the atrial fibrillation, right? Or ventricular fibrillation. Why it doesn't happen? Potassium in the blood is extremely tightly regulated. And this sodium-potassium pump is one of the mechanisms to constantly maintain low potassium concentration in the extracellular fluid, including plasma. Does that make sense? It's not the only mechanism of potassium excretion, but it's one really important, big mechanism. Because if you remember your AP1 ion concentration story, told you before, you need to know the concentrations of 4 ions: sodium, potassium, calcium, and chloride. Which 3 ions have higher extracellular concentration? Sodium, calcium, chloride. And potassium has higher intracellular concentration. So there are multiple mechanisms in place to maintain that relationship. And sodium-potassium pump is one of them. Does that make sense? So we're going to come back to that reabsorption story, over again. But now I want to talk to you about the concept of transport maximum. Ions, glucose, and amino acids, they use carriers and pumps in order to cross the membrane. Does it make sense to you? Does it make sense that those carriers and pumps have limited flow capacity? Do you understand what I'm trying to say? Let's say you have sodium-potassium pump. It can pump only so much potassium in a minute. You have sodium channel, it allows only so many sodium ions to get through in a minute. Does that make sense? So if, let's say, hypothetically, you have a system for sodium reabsorption that allows 100 sodium ions to cross one cell in a minute, if you will start to saturate, filtrate with more and more sodium, you understand what I'm saying? Your cells will not be able to reabsorb them all. You will start to excrete it. It is reflected on this graph. So blue is basically the reabsorption graph for a particular ion. On the x-axis is the concentration, that is for glucose, concentration of glucose in the blood. And on the y-axis is parameters in the filtrate, in the kidneys. So here's what's going to happen. Look at this. If you will start eating sugar, the amount of glucose that will be in your plasma will start to rise. Does that make sense to you? Since the amount of glucose in plasma increases, the amount of glucose in the filtrate will increase proportionally to it as well. Does that make sense? So say if you have plasma concentration of 600, then corresponding filtrate concentration will be 700. We're clear? Glucose, is it reabsorbed? Yeah. Huh? Bingo. So if you are in the range, like until 250 milligrams per 100 mil, okay? All glucose that is filtered, the red line, will be reabsorbed. The blue line. Does that make sense? At about 250, 300, the capacity to reabsorb glucose reaches its maximum. You cannot transport any more glucose back. But the amount of glucose in the filtrate far exceeds your reabsorption capacity. Does it make sense? So you will be reabsorbing about 400 at the level of 400, milligrams per 100 ml glucose, and all the excess, where will it go? Say it again? No, I'm talking about, you have certain amount of glucose in the urine, in the filtrate, you have a lot of it. Not all of it you can reabsorb. So the extra, where will it go? You'll pee it out. It's in the urine. Does that make sense? Here's the deal. You have 800 grams of glucose in 100 mils of filtrate. But you can reabsorb only 400 out of it. What's the difference? 400. You're going to lose it. Does that make sense? Now, remember we were talking about a hormone called insulin. And I showed you the image of glucose tolerance test. When you drink a bolus of glucose, and your blood glucose first goes up and then goes down. Remember that picture? Something like that. Okay? So for a person with a healthy pancreas and a healthy insulin metabolism and everything, person without diabetes, this will be at about 200. So fasting glucose is about 100. This is about 200. Does that make sense? Glucose levels for the person with diabetes at the peak of GTT can easily be 800. This level, it's impossible to reabsorb all the glucose that is filtered out in the filtrate. So glucose will be passed out with the filtrate in the urine. That is reflected. Here's the green line, the excretion. Does that make sense? How can you test that the patient, you have no equipment whatsoever, zero, no measurement, nothing. You suspect that, you have a patient in your hands that has diabetes. How can you check? The easy method and the hardcore method. Huh? Well, you don't have to drink, you can taste. Yes. It's the hardcore method. And the easy method in the summer. Stick it out on the windowsill. Flies. They love sugar. That was pretty much the old method to detect diabetes in patients. The urine that attracted more flies was always sweeter. Because flies actually don't like urine. There's not much nutrients there, it's not really nutritious stuff compared to feces, for instance. Now, not all the chemicals have this saturation type response. Do you see the blue line? Do you understand the term saturation? So at the transport maximum, the transport capacity is saturated. We clear? For sodium, for instance, it's called gradient time transport, which basically means you can increase this, you can eat as much sodium as you want. All of it is going to be reabsorbed. Okay? It's all about the difference. If you have, so the capacity of your kidneys to reabsorb sodium is so great that it's all going to be reabsorbed back. Does that make sense? Secretion, I can tell you up front, I don't really ask much about the secretory processes. Most of the secretion in the proximal convoluted tubule, okay, right here, hydrogen ions and ammonia. What's the importance of secreting hydrogen ion and ammonia? What do you regulate when you secrete, when you get rid of hydrogen ion? What do you regulate? Acidity. It's the regulation of acid-base balance. That makes sense? Drugs, urea, a lot of urea is secreted in the distal convoluted tubule, actually. Potassium is regulated by aldosterone. It's a distal convoluted tubule. Okay? So, secretion happens all over the place. What I want to highlight, there are a few substances that are secreted that I want to mention. Various drugs. Okay, and I'll get back to the drugs. Urea and uric acid. Urea and uric acid, they are passively reabsorbed. Remember when we talked about how sodium reabsorbed, water follows it with osmosis, urea concentration in the filtrate increases and urea gets reabsorbed. The whole point of your renal system is to get rid of urea. Do that make sense? So that's going to be secretory part. And as I mentioned, potassium. Okay. Now, secretion of hydrogen ions or bicarbonate allows you to regulate the pH of the blood. So basically, we've got like what? Potassium, urea, acid, drugs. Drugs have a particular importance from the standpoint of employment. People who worked in the renal physiology research have the best chances to find the job in the pharmaceutical companies. Because for any drug, you need to know how it behaves in the human body, how fast it is excreted in the urine. And that's renal physiology. Does that make sense? People actually measure. For instance, penicillin has a very quick, it is secreted very quickly. You know that if you ever took penicillin, you take a pill, an hour later you go to the restroom and your pee smells penicillin. Does that make sense? Your kidneys get rid of it right away. This is why you have to take it like 3 times a day to maintain the high concentration in the blood. No. We're not going to start that. No. Just, it's impossible. Now, however, I will ask you to